The following audiobook contains AI-generated content and may contain errors. My Audiobooks.ai presents Hoover Dam's Hidden Systems, 7 Engineering Choices Behind Its Enduring Design. Hoover Dam is usually remembered as a monument, a wall of concrete, a symbol of ambition, a landmark of the American Southwest. But the real drama is hidden inside it. Its survival depends on coordinated choices in concrete, steel, water, and rock. Congress authorized the Boulder Canyon Project in 1928. In the early 1930s, the United States Bureau of Reclamation built Hoover Dam in Black Canyon, where the Colorado River cuts through hard canyon walls. The question was never simply, how do you build something enormous? The harder question was this: how do you control heat, water, force, seepage, and future maintenance inside one structure, while a major river keeps trying to reclaim the site? The answer is not a single heroic gesture. It is 7 engineering systems working together. Some are visible from far away. Others are buried inside concrete, hidden behind gates, or pressed into the rock under the dam itself. The Boulder Canyon Project had several jobs at once. It was meant to reduce destructive flooding, store water over long periods, support irrigation, regulate downstream flows, and generate hydroelectric power for a growing region. Those purposes created a design problem with no room for a simple answer. A dam that stores a large reservoir must resist a steady push from water. That pressure grows with depth, so the lower part of the structure carries the hardest load. The site matters because the dam is not acting alone. The canyon, the foundation, and the concrete all become part of the same force path. Black Canyon offered a narrow gorge with strong walls composed of interbedded volcanic and sedimentary rock. That geology made an arch-gravity dam feasible. This is the first hidden decision. Hoover Dam is shaped to combine 2 different dam strategies. A pure gravity dam relies mainly on weight. Its own mass resists the reservoir pushing against it. A pure arch dam depends more heavily on curvature, sending water pressure sideways into the canyon walls. Hoover Dam uses both ideas at once. Its curved shape helps transfer part of the reservoir load into the prepared canyon rock. Its massive concrete body also presses downward into the foundation, using weight and contact with the ground to resist movement. The dam is not merely a block stopping a river, it is a force-routing machine. More concrete would add weight, but without the right shape and the right rock, the water would still search for weaknesses. The arch-gravity form turns the canyon from scenery into structure. The walls become active participants. The abutments were excavated to reach sound rock, with steps and keys cut into the canyon walls to receive the concrete blocks, forming interlocking contacts that resist sliding and distribute loads. This also explains why site selection was not just a matter of convenience. A wider, weaker canyon would have forced a different design logic. Black Canyon gave engineers a place where geometry and geology could work together. The dam reaches roughly 700 feet above the riverbed, with a crest length on the order of 1,200 feet. These dimensions had to satisfy both hydraulic storage needs and structural feasibility given the canyon geometry and available materials. The result is a dam whose visible curve is not decorative, it is a load path. The reservoir presses on the upstream face, the concrete receives that pressure, and the shape sends forces into rock that had been chosen and prepared to take them. As a result, the next system has to be solved under the constraints created by that mass and that shape. Once the dam's strength depends on massive concrete and strong rock, engineers have to manage the heat produced as the concrete cures. Concrete looks cold and inert once it hardens, but fresh mass concrete is chemically active. Cement hydration is an exothermic reaction, meaning it releases heat. In a sidewalk or a small wall, that heat can escape without becoming a central design crisis. In a dam made from millions of cubic yards of concrete, the large volume and low surface-to-volume ratio make it difficult for heat to escape. The interior can stay hot long after the outside has cooled. That temperature difference matters. If the outside contracts while the inside remains warmer, stress builds inside the concrete. Uncontrolled stress can lead to cracking, and cracking in a major dam is not a cosmetic problem. It can affect durability, create seepage paths, and alter the long-term behavior of the structure. Hoover's second hidden decision was temperature control. The dam was not poured as one giant monolith. Construction proceeded block by block and lift by lift, with planned contraction joints dividing the concrete into manageable sections. The concrete mixes were carefully controlled, materials were pre-cooled, and the designers used low-heat cements and pozzolanic materials to reduce thermal output during hydration. A refrigeration plant at the site supplied chilled water. A major part of the system was embedded steel conduit. Roughly 585 miles of steel conduit, with lines about 1 inch in diameter, were placed inside the dam so chilled water could circulate through the concrete. The dam was cooled from within. Early cooling phases even used relatively cool water from the Colorado River before the dedicated refrigeration plant was fully deployed. This system lowered internal temperatures, reduced the risk of thermal cracking, and helped construction move faster than natural cooling would have allowed. Construction slots, intentional vertical gaps left between portions of the structure, were closed later after adjacent blocks had undergone initial cooling and contraction. This reduced restraint and cracking potential. There is a common claim that Hoover's concrete would have taken an extremely long time to cool naturally. Treat that as a simple illustration of the heat transfer problem, not as the complete story. What matters in the record is that engineers used placement sequencing, joints, concrete control, pre-cooling, embedded conduit, chilled water, and refrigeration as one coordinated thermal strategy. Cooling the dam addressed the concrete after it arrived. Before concrete could become the dam, the river itself had to be moved out of the way. That is the third hidden decision: construction sequencing. Hoover Dam was built by managing time as carefully as stone, steel, and concrete. The sequence had to be deliberate. Diversion tunnels were driven through the canyon walls so the Colorado River could be routed around the construction site. Then the river was sent through those alternate paths. Cofferdams were built to block water from the working area, allowing the foundation to be dried, cleaned, and prepared. Only after that could the main dam rise. Finally, the diversion system had to be closed or converted into permanent operation as the completed hydraulic works took over. Each step depended on the one before it. If the river was diverted too late, the work area could not be prepared. If the temporary barriers were too weak, seasonal flows could overwhelm the site. If the temporary works had no relationship to the permanent system, engineers would be solving one problem while creating another. Seasonal floods made timing dangerous. The tunnels, cofferdams, outlet works, and dam construction schedule formed a single choreography. Once the dam is complete, the central problem changes again. The project is no longer trying to keep water away from the construction site. It is trying to control water forever, including water that arrives during extreme floods. A working dam cannot be designed only for average conditions. Ordinary reservoir operation is one challenge. Rare floodwater is another. If floodwater rises high enough to overtop a dam, it can attack surfaces and foundations in ways the main structure was never meant to endure. That is why spillways are essential. Hoover's fourth hidden decision is hydraulic energy management during extreme events. Spillways give excess water a controlled route instead of allowing it to pour over the crest in an uncontrolled sheet. A spillway is not just an overflow path. It must handle water with enormous potential energy. Water dropping from reservoir height can become destructive if it strikes the wrong place with too much force. The design problem is to turn a dangerous drop into managed turbulence and a downstream release that the system can survive. Hoover's spillways and outlet systems are tied to basin-scale flood considerations. They protect the dam by providing routes for rare flows, not just by supporting daily operation. Reliability means the structure has a plan for unusual water, not only normal water. That principle leads into the fifth hidden decision, the internal water delivery path. Once water is stored behind the dam, it can be released, regulated, or used to generate power. The route begins at intake towers, where water enters the system from the reservoir. Gates and valves control admission and flow. Penstocks carry the water under pressure. Turbines convert moving water into mechanical rotation. Generators then convert that rotation into electricity. This sequence sounds simple only if the dam is imagined as a wall with pipes through it. Hoover is more complicated. It is a controlled hydraulic machine with multiple operating modes. Power generation and river regulation are linked because the same water system supports both. Water sent through turbines can produce electricity while also contributing to downstream releases. Other outlet works can help manage flows when power generation is not the only objective. The dam's operating logic connects reservoir storage, release timing, mechanical equipment, and downstream needs. That connection is central to Hoover's influence. A storage dam with hydroelectric capacity is not just holding water for later. It changes when water moves, how quickly it moves, and what useful work it can do during the journey. The engineering challenge is control. Water must enter through the right openings, travel through pressure pathways, spin machinery without destroying it, and leave in a managed way. Every gate, valve, intake, penstock, turbine, and outlet participates in a larger system of restraint and conversion. Spillways reveal one side of that philosophy. Prepare for excess water. Penstocks and turbines reveal another. Use controlled water as an energy source. Together, they show that the dam's purpose is not to defeat the river in a simple sense. Its purpose is to make the river legible, adjustable, and useful under changing conditions. Even the best designed hydraulic system ages. Concrete moves slightly. Water finds paths. Loads vary. Equipment needs attention. A dam expected to last cannot be sealed up and forgotten. It has to be inspectable from the inside. The sixth hidden decision is the gallery network. Inside and around a major dam, galleries are working passages. They allow people to inspect, operate, drain, measure, and maintain the structure over time. This can be overlooked because the public image of Hoover Dam is exterior scale. The inside matters just as much. Hidden passages make the dam readable. Engineers can inspect joints, check signs of movement, manage drainage, and work near systems that would otherwise be unreachable. Instrumentation extends that idea. A large dam is not judged only by how it looked on opening day. It is judged by how it behaves across decades of reservoir cycles, maintenance campaigns, upgrades, and changing safety expectations. Measurement turns the structure into a long-term source of information. By tracking thermal gradients, stress distributions, and seepage flows, engineers can verify whether original design assumptions still hold. Drainage is especially important. Water pressure inside or beneath a dam can change the forces acting on it. Internal pathways help manage that pressure and reveal whether water is moving where it should not. Inspection access gives engineers a way to respond before small issues become larger ones. Later, monitoring and modernization continue the same principle. New instruments, revised operating practices, and upgrades do not replace the original idea. They extend it. The dam must remain observable and serviceable. This is a quieter kind of engineering than concrete placement or river diversion, but it can be the clearest sign of long-term thinking. Monumental infrastructure survives when designers assume that future engineers will need access, data, and room to work. Longevity is designed into the structure through inspectability. Hoover Dam is not only a finished object, it is a maintained system, with hidden spaces that allow each generation to keep reading its condition. But the deepest part of that system is not inside the concrete, it is under it and beside it, where water, rock, and force meet. The seventh hidden decision is foundation treatment and safety by design. An arch-gravity dam works only if the rock beneath and beside it can safely receive the loads. The canyon walls and foundation are not passive background. They are structural partners. The physical risk is straightforward. Water under pressure can move through fractures, seams, and weak contact zones. Beneath a dam, that pressure can push upward. Engineers call this uplift. If uplift is not controlled, it can reduce the effective weight holding the dam in place. Water can also increase seepage, exploit cracks in rock, or weaken the contact between concrete and foundation. Hoover's safety strategy includes rock preparation, grouting, drainage, contraction joints, seepage control, uplift control, and later seismic hardening. These measures are not decorative add-ons. They address specific ways a dam can lose stability or durability over time. Grouting helps reduce unwanted water movement through fractured rock by filling selected paths under pressure. Drainage gives water pressure a managed way to relieve itself, preventing it from building up beneath the structure. Prepared rock provides a better contact surface for the concrete. Contraction joints help the massive structure accommodate thermal and structural behavior in a controlled way. Later hardening reflects the continuing need to reassess infrastructure as knowledge, standards, and technology change. Exact uplift and stress distributions depend on modeling assumptions, reservoir conditions, material properties, and how engineers represent the dam foundation system. Even so, the documented risk reduction strategy is clear. Hoover Dam treats the foundation as part of the dam. This brings the story back to the first decision. The arch gravity form can route reservoir forces into the canyon only if the rock is capable of receiving those forces. The shape, the mass, the joints, the grouting, the drainage, and the monitoring all depend on one another. Seen this way, Hoover Dam is less like a single wall and more like a network of cooperating solutions. The canyon geometry routes force. The concrete cooling system controls heat. The diversion sequence controls time and river access. The spillways manage rare floods. The intakes, valves, penstocks, turbines, and generators turn regulated water into power and releases. The gallery network keeps the dam inspectable. The foundation treatment manages seepage, uplift, and the contact between concrete and rock. That is the deeper reason Hoover Dam still matters as an engineering landmark. Its importance is not only that it is large, famous, or visually imposing. It shows how a public work becomes durable when many specialized systems are made to support the same purpose. The monument is what people remember. The system is what makes the monument possible. If this changes how you think about Hoover Dam, carry the question outward. How many other monuments are really bundles of hidden systems? The next time a structure looks simple from a distance, ask what invisible choices are keeping it standing. This concludes the